You've done it, I've done it, we've all done it. You type a question into an AI, you hit enter, and you watch the answer just magically appear. But have you ever stopped to think what's really going on in those few seconds? Well, today, we're going to pull back the curtain on that digital magic.
Yeah, seriously. Think about the last question you asked an AI. It feels instantaneous, doesn't it? Just boom, there's your answer. But underneath that clean, simple little interface, there is an incredibly complex, high-speed race happening. And today, we're going to follow your question on that exact journey, step by step.
So the easiest way to wrap our heads around this whole thing is to picture an answer assembly line. You know, like in a factory. Your question is the raw material that comes in one door. It gets passed down this line, with each station doing a very specific job, until a fully formed, polished answer rolls out the other side, right back to your screen. Okay, so this answer assembly line is a great way to think about it. But in the AI world, it has a technical name, the inference pipeline. And honestly, if you can just get your head around that one word, inference, you've pretty much unlocked the secret to this whole process. Now, this is a really, really important distinction. We hear the word training thrown around all the time, right? And that's like the AI going to school for years. It's studying for the big test, reading every book in the digital library, just learning, learning, learning. But inference? That is the test. It's game day. It's the moment you ask a brand new question and the AI has to use everything it's learned to give you an answer right here, right now. So here's the bottom line. Inference is the AI in action. It's not in study mode anymore, it's in performance mode. It's the live, real-time process of actually using its knowledge to generate an answer. It's the AI, well, doing its job. All right, so let's get back to our assembly line. Your question has just arrived at the factory door. What's the very first thing that happens? Well, it needs to get sorted, and someone's got to make a plan for how to handle this new job. And to make this super clear, let's follow a real example. Let's say you type in a financial question, something like, what is the trend of Nifty? Seems simple enough, right? But that one little sentence is about to get pulled apart and analyzed in a big way. And here's that first handoff in action. First, your human words get chopped up into something called tokens. That's just machine speak. Then it hits the router. Think of the router as a super efficient receptionist. It takes one look at your question and goes, okay, financial stuff, and immediately sends it to the right team. Right after that, it goes to the planner, who's basically the project manager. The planner looks at the job and breaks it down into a simple to-do list. So for our question about Nifty, the planner's little to-do list would look something like this. Step 1, fetch the market data. Step 2, analyze that data for a trend. And step 3, summarize what you found. Boom! That's the blueprint. That's the plan of attack for building our answer. Okay, so we have a plan. We know what we need to do. Now it's time to gather the raw materials to actually get the job done. Welcome to the next station on the assembly line. And this station is run by the retriever. I love this analogy. Think of it like a research librarian on a triple espresso. Its only job is to sprint into the digital archives. We're talking databases, documents, real-time data feeds, and grab every single piece of relevant information. For our Nifty question, it's going to go find all that historical market data. And now all these different pieces get assembled. They all get bundled up into one final set of instructions that's sent to the AI's core brain, the large language model. We call this the prompt, and it's really just a simple recipe. You take some system instructions, you add the context our librarian just found, and you top it off with your original question. That's it. That's the complete package. Okay, the prompt is built. The instructions are ready. We've now arrived at the main event. This is the heart of the entire operation, where the real thinking happens. We're talking about the large language model, or LLM. So what's actually going on inside this LLM? It's not some kind of mysterious magic. It's actually just really, really fast math. It takes that whole prompt we just built, and it uses a cool mechanism called attention to figure out which words are the most important. Based on that, it makes a prediction, a statistical guess for the most probable next word. And then it just does that again, and again, and again. It's literally building the answer one word at a time in this super fast loop. But, and this is super important, the LLM isn't just locked in its own brain. It has backup. If it needs to know something that's happening right now, or if it needs to do some serious number crunching, it can call for help. It can use tools to run some code, maybe query a database directly, or even ping an external financial service to get the absolute latest up-to-the-second stock price. So you've got this incredibly complex assembly line, right, with all these moving parts. The final piece of the puzzle, and maybe the biggest engineering challenge of all, is making this whole thing work in the blink of an eye and, not have it fall apart. And this is why all of this really matters to you, to me, to anyone using these tools. The speed of this pipeline, it's everything. It's the whole ballgame. Because engineers are fighting for every millisecond. And the difference between a 2-second response and a 10-second response is the difference between something that feels like magic and something that's just frustrating. So what are their tricks? How do they make it so ridiculously fast? Well, here's a peek at the engineering playbook. They use caching, which is just reusing old answers so you don't have to do the work again. There's parallelization. That's a fancy word for doing multiple things at once, like planning the job and grabbing the data at the exact same time. They optimize tokens to keep things small and speedy. And they use these really clever tricks like a KV cache to help the AI remember its thought process so it doesn't have to start from scratch every single time. It's all about shaving off every possible millisecond. But of course, with a system this complex, things can definitely break. The receptionist, our router, might send your request to the wrong department. The librarian, the retriever, might run back with the wrong set of books. The model itself can just make stuff up. That's what we call a hallucination. Or one of those external tools that calls for help might just be offline. A really well-built pipeline has to be ready for any of this to fail at any moment. And that brings us to what makes a good pipeline. These are kind of the blueprints for success. First, it has to be modular. Think Lego blocks. Each piece is independent, so if one breaks, you can just swap it out. It has to be scalable, so it can handle me, you, and a million other people asking questions at the same time. And it's got to be reliable, which just means it has a plan B for when things inevitably go wrong. So look, if there's one thing to take away from all this, it's that the instant answer you get isn't instant at all. It's the end result of this incredible, high-speed ballet of software. A pipeline that's routing, planning, gathering data, and executing a response all in a fraction of a second. It really is a masterpiece of modern engineering. And I'll just leave you with this thought. You could build the most powerful, intelligent AI model in the entire world, but without an efficient, lightning-fast inference pipeline to back it up, that model is basically useless. That intelligence is just locked in a box. It's the pipeline, that answer assembly line, that truly brings AI to life. Thanks for coming along on this little journey behind the curtain.